состояние, очень существенно отличается от расстояния между первым возбужденным и вторым возбужденным. Поэтому такие кубиты можно очень быстро манипулировать такими кубитами квантовой системы. Почему? Потому что если мы светим на этой вот частоте светим микроволны, мы приготавливаем суперпозицию в состоянии 0 и 1. Но при этом частота радиосвязи, эволюция этого состояния, она будет происходить со скоростью, которая пропорциональна амплитуде приложенного сигнала. Если у нас явится фазовый кубит, у которого ангармонизм маленький, на расстоянии между 0 и 1, всего лишь чуть-чуть больше, чем на расстоянии между 1 и 2, то в случае, когда частота радия становится порядка ангармонизма, то есть разница между частотами 0,1 и 1,2, неизбежным образом возбуждаются более высокие состояния. То есть мы уходим как бы из множества состояния 0,1, мы начинаем попадать в состояние 2. Это означает, что у нас уже система не двухуровневая, что у нас возникает много уже дополнительных состояний в системе, и это уже не является кубитом. Потоковый кубит, он замечательный тем, что здесь можно очень сильно большой амплитудой возбуждать переходы между 0 и 1, и при этом из-за сильного ангармонизма более высокое состояние возбуждаться не будет. Это очень здорово, означает, что можно квантовые вещи делать очень быстро. Ну, а начать я вам коротко рассказал про то, как связывать кубиты, и то, что я на самом деле фактически пропустил, но я оставлю эти слайды для того, чтобы можно было посмотреть, может быть, оригинальные работы. Вот они какие-то приведены. Это работы, в которых были показаны первые вентили двухкубитные на такой системе. Ну, в данном случае здесь 2 кубита, 2 управляющих катушки, 2 считывающих скрида. И делался вентиль здесь символ. И дальше я показывал вам, вот это я не стал показывать, но как бы оставлю в конце, только коротко скажу. Здесь, в принципе, была сделана довольно важная работа Аркадием Федоровым, который был профессором в Австралии, в Брисбене, в университете Южного Александра. Вот, в то время, правда, он был в Брисбене. Вот. Здесь идея была в том, чтобы сделать потоковый кубит, у которого величину щели между 0 и 1 можно менять. А это достигается при помощи изменения коэффициента альфа. Как это сделать? Вместо маленького перехода, который находится здесь, сюда вставляется маленький сквидик. И локальный магнитный поток, который будет подведен как бы сквидик, который будет менять магнитный поток в этой дырке. В первую очередь, а во вторую очередь уже как общий магнитный поток. В этом случае коэффициент альфа будет переменен. Означает, что можно изменять ничего. Такие эксперименты были сделаны успешно. Вы видите здесь на правой картинке снят спектр потокового кубита. Это магнитное поле, магнитный поток, это частота. Здесь он щель всего лишь там порядка гигагерца, а вот тут щель она уже существенно больше. 5 гигагерц. Вот такие системы успешно использовались в экспериментах для демонстрации квантовости такого объекта. Вот. Но об этом я сегодня уже говорить не буду. Значит, я сейчас перейду к свежему материалу, к сегодняшней лекции. Хотел сказать, что на сети, значит, у вас на страничке, которая связана с курсом, все предыдущие лекции выложены. Вот, можете посмотреть, вчера подтвердила, что она все получила, должна была выложить. Я туда же положил несколько обзоров по циркулярному кубиту, не только по ним. Вот, поэтому, пожалуйста, смотрите, это очень полезный материал, который можно использовать для того, чтобы получше сориентироваться в этой совершенно новом области. К сожалению, книжек пока на эту тему таких систематических нет. На русском языке есть книжка моего коллеги Ильичева по циркулярниковой кубиты, но она довольно мало изображен, было написано, ее действительно можно найти в английском языке. Но они немножко уже, актуальность, потому что область очень быстро развивается. На курсе я попытаюсь вам, с одной стороны, увидеть, дать вам возможность видеть историческую перспективу, которая была обязана циркулярной кубитой, а с другой стороны, все-таки показать вещи. From this point, I will switch to English. This is
А можно, пожалуйста, все-таки по-русски читать лекции? Так сильно понятнее.
Если вас не видно,
Ну, прям на порядок. Но читать статьи можно со словарем.
Демократия предполагает, что меньшинство диктует свои правила большинству. Ну нет, просто говорит, что согласно демократии, у меня есть компромиссное решение. Я слайд все
Да. Очень странно просто складно смотреть на английском, читать на английском, изначально.
на английском.
Хорошо, давайте сделаем так. Я все-таки буду читать по-английски, как меня просили. А все вопросы и обсуждения я готов и делал. Я думаю, что это будет все-таки.
Спасибо большое. Какая же демократия?
Я вам рассказывал, что, например, на семинаре
Помните делать компромиссы по лекции?
Сегодня мы все-таки начнем говорить о новой теме, поэтому я хотел понятие на языке. Вопросы, как мы говорим.
А у вас в Zoom трансляция презентации не включена.
Today we have about both online. So you see here in light gray what we have already done. This should be all now. So we talk about today about charge qubits and circuitry. And the second lecture today is going to be about transform.
Извините, пожалуйста, а вы не могли бы еще звук включить? У вас звук выключен в Zoom.
У меня включен вебинар.
у вас
Да, там микрофон выключен.
у вас микрофон.
Да, микрофон выключен. Ну, в смысле, вас в Zoom не слышно.
Левая кнопка unmute. Слева. Да, значит микрофон.
Спасибо вам. Что-то я совсем какой. Равновременной презентации хоть в этом не учится уже третий год, но тем не менее забываешь иногда. Окей. This is an overview of superconducting qubits. If you want, this is a genealogical tree, which is not connected, but it has a few samples of the genealogical tree. There are many species of superconducting qubits. Много видов проводниковых qubits. Historically, the very first one was the charge qubit. And that's something we are going to discuss today. And we discussed already the historically about the same time, but a little later was the flux qubit. These are the two basic types. For you, it's very important to understand that they are on two different limits of quantumness, so to say, of uncertainty of superconducting circuits, which is characterized by the phase difference on the quantum junction and the charge in the small island. The uncertainty is that the product of uncertainty in number of particles is cannot be arbitrary. It's always Planck's constant divided by uncertainty in the phase. This is something we already discussed, the phase qubit, and the transformation of the phase qubit in a way is the transform, which we'll discuss later today. And then in the following lectures, we'll also talk about fluxonium, which, as many people, including myself, believe will be most probably the qubit of the qubit which will heal the drawbacks of transform qubits, which are now being used for most of quantum computing circuits. Okay, we'll talk about charge qubits, and then very important, we start talking about circuit QED. Circuit QED is a Swiss knife. Швейцарский нож. Универсальное устройство для того, чтобы измерять циркульный. Let's take a general attitude. So we talk about Cooper pair box. Cooper pair box is a superconducting island, which is a very small one, which is connected to a bulk superconductor with a Josephson junction. So this is a bulk superconductor. This ground is just a superconducting block with a lot of electrons there. This is a small Josephson junction, which connects a small grain, how small, few tenths of nanometer in size. So this capacitance is obviously quite small because the grain is very small and therefore the junction is also very small. This is the symbol for Josephson junction. So basically you have a piece of superconductor, you have a tunnel barrier, and then on top you have a little grain. And you can control this the charge of the grain by applying a gate voltage. So this is your gate voltage which you apply. When you apply a gate voltage, you polarize charges on metallic electrodes. So altogether this metallic electrode. But electrons, they can be polarized, which means that they will accumulate on this island only under condition that they tunnel through the tunnel junction. So they tunnel from here to there. However, there is the fundamental characteristic energy there, which is the charging energy, which means that if you want to transfer one Cooper pair from this part to that part, you need to overcome the energy, which is written here, which is square of the charge divided by twice capacitance. And this is a square of the charge is, of course, the Cooper pair charge square. And the capacitance here is a combination of the two capacitances, which is the CJ, the capacitance of the junction, and the capacitance of the gate. So altogether, this thing is called the charging energy EC. And then if you polarize this, the charges in this the system here, then the charging energy, which is shown here in the vertical axis, is depending on the charge, on the polarization charge which you induce. It will be basically a parabola, because this is a square of the charge, so it will be a parabola here. The energy as a function of the gate voltage, or which is proportional, of course, to the polarization charge. However, if you take by hand the Cooper pair and you bring this on this island, then this whole parabola will be shifted. So the minimum energy will be exactly one extra charge on this island. On this island, you have billions of electrons. So we talk about some extra charges which will modify the charge neutrality of this island. It will be not charge neutral anymore, but it will be containing a single electron charge. And then if you put two Cooper pairs, then you have this curve here. If you put three Cooper pairs, you will have this curve. So this factor n is basically a number of Cooper pairs on the island there. Okay. Suppose you have no tunneling here. If you have no tunneling, then of course these all curves, they are not connected because they correspond to different states. If you have by chance zero Cooper pairs on the island, you have this curve. Of course, it also goes to negative direction here. If you have one, you have this curve. You have two, this curve, and so forth. However, when you allow for tunneling of superconducting electrons, that means that in this point here, you have two states, possible states on the island, with zero Cooper pairs and one Cooper pair. And these two states, they will be now not completely disconnected. They can be connected because this Cooper pair can tunnel through the Josephson junction. And as often happens in quantum systems, once you have two interacting or two types of energy contributions, and these energy contributions are associated with non-commuting variables. Here, these variables are charge and the phase. Charging energy depends on the charge, and Josephson energy depends on the phase. It's proportional to this one times cosine phi of the phase difference here. Then at this crossing point, the degeneracy is lifted. What means the degeneracy is lifted? If you have the interaction, and you have the interaction between the states because you allow for tunneling of Cooper pair through the island, that means that you'll have not just crossing points with non-interacting parabolas here, but you have now, like you have also in the band structure of solid and many other examples of quantum physics, you have here a gap. And this gap is exactly the Josephson energy, which comes out due to this tunneling. So the lowest energy state becomes now this periodic state in charge. Okay? And the first excited state becomes this state. Of course, there are also gaps at higher energy, which should be the gap between the first excited and the second excited state, and so forth. The Hamiltonian of the system is written here. It contains the charging energy, and it contains the Josephson energy. And if you basically diagonalize this Hamiltonian quantum mechanically, you'll get this band structure. This is the picture of this energy band, which are so to say, the quasi-charge space. So if you increase the charge by increasing the gate voltage, then you'll have this band structure here. And obviously, once you have this splitting here, then the lowest energy state is the symmetric superposition of the state with zero Cooper pair and the state with one Cooper pair, which is this state here. So you have exactly 50% of the state zero Cooper pairs and 50% of the state one. The first excited state will be antisymmetric superposition of the two states, which were decoupled, but now the degeneracy is linked. So in the system, basically, you have a Josephson junction which lifts the degeneracy of the charge states, which otherwise are not coupled. And this is the essence of the charge qubit, which was initially it was actually developed. The ideas of that were developed here in Moscow by Konstantin Konstantinovich Likharev and his school. This was кафедра колебаний МГУ, где они еще в 80-е годы задумались, собственно, о вопросе, а что будет, если вот сделать такой маленький островок. И была целая серия работ, пионеры в этой области являются признанными в мире Лихарев и Зорин. Лихарев, он уже на пенсии и живет в Америке, был много лет профессором в университете Нью-Йорк, а Александр Зорин долгое время работал в Германии, тоже уже на пенсии. Вот. Но те фундаментальные работы были сделаны тогда еще в Московской школе теоретической физики, и именно многие работы по физике ньютоновских переходов на самом деле произошли отсюда. Okay, so let's move on. Now, let us discuss a little bit the two variables I mentioned already. Basically, there is a charge which is associated with the number of Cooper pairs on the island. This is characterized by this operator n, and the phase is the phase operator. And if you can calculate the commutation relation, then it's non-zero. It's non-zero. That means that you cannot measure simultaneously the two physical variables with arbitrary accuracy. You have to work with this with quantum uncertainty as you do with momentum in space, space coordinate in mechanics. So the energy eigenstates will be then 0 and 1. And as I said, for example, the state 0 at 0 charge is going to be purely, nearly purely 0 Cooper pair state. But if you go to the half Cooper pair charge, which means to charge of 1 electron, this is here. This is the point when you polarize by gate the charge to 1 electron charge. Then you have equal share of 0 electron state and 0 Cooper pair state and 1 Cooper pair state on the island. So you basically can go from the basis of number of Cooper pair states to more appropriate basis for this Hamiltonian with interaction, where you have 0 and 1, the eigenstates of the system. However, if you prepare the system in this point here, and you rapidly move the charge by applying a voltage pulse here to this point, what will happen? Who knows? Superposition would be. There will be superposition, that's correct. But what will happen dynamically? Will the charge stay constant or not on the island?
Если будет суперпозиция куперовских пар, то не будет динамика, space времени.
The answer is if you do this very slowly, adiabatically, nothing will happen.
Не будет перехода.
If you do it adiabatically, you will stay in the ground state. Okay? But if you do it rapidly, then what you do, you start from the state of the Hamiltonian, of this half of Hamiltonian, which is not the eigenstate. So if you are here with a charge on with a 0 Cooper pair charge, then you prepare the state of the Hamiltonian, which is not the eigenstate. What happens with the non-eigenstate of the Hamiltonian? It evolves in time, according to Schrödinger equation. So if you prepare the stationary state, the solution of the Hamiltonian, you prepare the eigenstate. If you can prepare the system here, nothing will change. You will stay in the ground state. But if you prepare the system and rapidly move from this point, then the system will evolve between these two states with the frequency exactly proportional to the energy difference, or exactly to say energy difference divided by Planck's constant. And this will be something like one more oscillation of the spin. Okay, so if you kick the spin, then the spin starts progressing. This is basically the same type of phenomenon. So if you prepare non-eigenstate of the Hamiltonian and non-adiabatically move here, then it will start evolving. There are many interesting things here. If you move very rapidly, what will happen? If you move this very quickly, who knows quantum mechanics? What will happen? Have you heard of Landau-Zeller tunneling?
Да, если очень быстро, то вообще там просто возможно будет переход на первое состояние.
So if you do it much faster, if you move much faster, then the inverse frequency of the splitting, you will stay in this state. You have no time to go over to the other state, right? So basically you will go to this branch here, if you do it very, very quickly. But if you stop here, then of course you do the oscillate quickly. So you start from this state and then you evolve in time in this way. So this is a very basic quantum mechanics, which of course you should know, and I believe most of you do. Then let's see how can we control the system. If we want to do something with the system, we of course need to have some nodes, some control nodes. And the most convenient control knob in our case is that the knob which allows us to change the Josephson energy. The Josephson energy of this junction is proportional to the critical current. You remember the Josephson energy maximum is critical current times the flux quantum divided by 2 pi. And it's proportional also, it depends also on the cosine of the phase difference here. So if you replace this junction by squid, then the Josephson energy of this entire element, Josephson energy which couples this island to the big piece of superconductor below, will be proportional to the cosine of the flux in this hole divided by flux quantum, of course, with the factor of pi. And in the introductory lecture a week ago, we discussed that in this case, the critical current of the squid will be changing like this, on the assumption that the inductance of this loop is is very small, much smaller than the inductance of individual junctions. And then basically, this is the dependence of the Josephson energy or critical current, but it's proportional to Josephson energy on the flux which you apply to the squid. So by doing this, basically, you can make the Josephson coupling equal to 0. In this case, the gap between the ground state and the first excited state will disappear. You will close the gap. But if you go here, for example, then the gap will be proportional to the critical current here, which you can control by the external flux. Okay, so this is basically a quantum system which can be controlled by charge on the gate and the flux applied to the squid. And people thought of this for a long time, and they were playing for a long time, from 1990 to about 1998 or so. There were many experiments trying to show the superposition of the charge states. And this was really kind of a very basic question. Can macroscopic charge states show quantum superposition or not? What will be the coherence of this quantum superposition, if it exists at all? And theoretically, it should be expected from the Hamiltonian, which we just introduced here, and from general considerations. But this was a really weird experiment because people at that time believed that quantum mechanics is not really applied to large objects, can be applied to small objects. Okay, if I take the large object, of course, you cannot take a brick and tunnel to the wall. The probability is very low, exponentially small, so you will never observe it within the time of the universe. However, if you prepare now many Cooper pairs and bring this into this whole framework, then the proposition was that it should exist, and the coherence time could be measured. And the first pioneering experiment, when this time was measured, was done in 1999 by these three people: Yasu Nakamura, Yuri Pashkin, and Shensai. They did it in Japan by just doing an amazing experiment, which I think was very courageous to try, but it worked. So what they've done, and this is the very first paper, the very first superconducting qubit ever demonstrated. Well, actually, I should, that time already, the microwave spectra of the qubits, which means these things, these lines, this is the energy and this is the charge, and this is the transition. So one can apply microwave frequency and see additional loss in the system if you hit the resonance between the two levels. And spectroscopy already existed at that time. However, this was the very first experiment when this was demonstrated really in the time domain. So what they've done was the following. They take this little, actually quite big, reservoir. This is a big piece of superconductor, if you want to connect it to the ground somewhere up there. Cooper pair box is this little bar, this very small bar, which has this tunnel junction and that tunnel junction. So this is the loop, the loop of the squid, which is required to change the Josephson coupling energy between this little island and the reservoir of Cooper pairs. Then this probe was actually an additional finger. So this was an additional finger which was made afterwards. This probe was made with a thick tunnel contact to the small grain here. And then this probe was just used simply to measure the charge on the island. So if there is a extra charge on the island, of course, there will be some panel current in the probe. Very brutal kind of approach. It's not really non-destructive. It's fully destructive measurement. So the charge state with this measurement on the island is destroyed. And then here there was the DC gate, which modifies the potential of this little island. In addition, there was also the pulse gate. Why they are different? Because the pulse gate was needed to apply very short pulses. And if you want to do it, then you have to pay attention to the shape of the electrodes, because you know that if you transfer very high frequencies and very short pulse will have high frequency components in it, then the biggest problem is the reflection from the region where there is a mismatch. So this whole line was connected to the coupler line, so it's like two grounds of the superconducting electrodes with a wire in the middle, and the impedance of this coupler was about 50 ohms. So this pulse gate was needed to apply very short pulses, which will modify the potential on the scheme. And this is what they measured. I will explain what they actually measured in the next slide. And this is what was the expectation from quantum theory. And the two pictures are very beautiful, and the agreement is stunning. This is the charge on this little island. This is time in picoseconds. It's very short time scale. And the color here is the proportional to the current which was measured by the probe electrode. Basically, the intensity here is proportional to the charge on this island. And as you see here, the charge at half of the Cooper pair charge on the island oscillates as a function of time. What they have done is in the next picture. So there was a series of papers, and they was followed the first Nature paper by more experiments. But what they did was very simple. So they were starting from this point, and then for a very short time, bringing the system into superposition between the ground state and the first excited state. They wrote it also here. Excuse me, between superposition between 0 Cooper pair state and 1 Cooper pair state in the R. And here, of course, they were arriving to this point. However, the initial state of the Hamiltonian which they prepared was not the eigenstate. Now, the eigenstate of this Hamiltonian will be superposition of 0 state and 1 state. And therefore, there was of course, expected to be an evolution of the system between this state and that state, with a frequency which is proportional to the Josephson coupling energy. When you have this evolution, then half period you are at this ground state, and then slowly you go to equal occupation of state 0 and 1, and then you go to the excited state. Once you are in the excited state, you can be either in the state 1 or the state 0. And therefore, the charge on the island can be, of course, also depending on the time you wait. So what they were doing was the following. It's illustrated by this picture here. First, they start near 0 point here, okay, and then they go with the pulse to this point, half Cooper pair charge, and wait there for the time delta t. And then in this point, the oscillations occur between the state 0, between the state of 0 Cooper pairs on the island and the state 1 Cooper pair on the island. And then if you go back and then you move away, if you are at this moment in the state 0, you will end up in this point. If you're in the state 1, you will end up at that point. It means that the charge, which will be remaining on the island, will depend on the time you wait. If you wait the whole period of oscillations, you will stay here. But if you wait only half of the period of the oscillations, you will be up there. And then this charge is measured by the tunnel junction. So once you pulse back, you go back here. Then the qubit is found either in this state or in that state, depending on the pulse duration, delta t. And that's exactly what was done in this experiment. This is Yasu Nakamura. who is actually an amazing guy. He didn't have a PhD at that time. Because he was so much in this experiment, he wanted to do it so much that he even didn't take time to finish his PhD. Actually, he went to do his PhD 2 years later to Delft, where people in the group of Hans Muth, whom I told you about in the previous story about flux qubit, they were about to make the coherent experiment with flux qubit, and he actually participated in both. And Yuri Pashkin, his role was largely that he made the nanostructure. So he was, he's a very, very skilled physicist and also capable of using very fine technology. He's now a professor in Lancaster in the UK. Anyway, so what they have done is exactly this. So this is again the same picture, like you have here a superposition state of the two charge states. And then if you go back, then you'll have either this state or that state. And these are the periodic oscillations which they observed, okay? This oscillations is nothing else as they cut through this line here. Let me go just the slides back. This is a cut like this in this line. So in particular charge, you have the oscillation of the current through the tunnel junction, depending on the duration of this pulse. Of course, you do this experiment by repeating it many thousand times. So you fix the duration of this pulse, which you apply, and then you repeat it many thousand times, and you measure the average tunneling current. Then you increase the duration of the pulse a little bit, and again you repeat it many thousand times, and again measure the average tunneling current. And then from the probabilistic nature of quantum mechanics, what you will measure will be these periodic oscillations. Interestingly, the time resolution here you see is about it's actually smaller than 20 nanoseconds. And when they did this experiment, they couldn't really measure anything on longer times. So what Nakamura did, he went upstairs at NEC. They had also semiconductor physics group, semiconductor devices, and he borrowed from them a very expensive pulse generator. It was in the price range of about $300,000 that time. And using this very short pulses, they were able to resolve this time scale. And when people around the world saw this experiment and really were very impressed, they started talking, okay, but if you don't have this very fast pulse generator, then you will never do this experiment. And if you want to repeat it, you need to get this pulse generator. And this is like, so the world was much nicer, because if you do this experiment better and people learn how to do it better and better, then the coherence times become longer and longer. And this first experiment, the coherence time was only in the range of about 1 nanosecond. So these oscillations, they were lasting only about 1 to 2 nanoseconds, very short. But this was really the pioneering experiment which showed this superposition of the charge states. So this decaying thing here was actually half a nanosecond here, but if you measure longer, then basically you measure average current and no oscillations anymore. All right. So what is the reason of this very short time? When people did this first experiment, nobody knows, of course, what is the reason. So you have to do more and more experiments, and more experiments were coming a few years after. So the main reason for the coherence in this experiment was the charge fluctuations. If you have some random charges here on the substrate, and the random charges, they appear, they are always, for example, we fabricate this nano circuit and then we take it to the air. Then the air and some other rays from the air, they go on the surface. And all this garbage, all this dust, all this dirt, it has some disorder nature, and in this disorder of nature, of course, there are some charges which can be localized or which can be simply jumping back and forth. And we know that this device is sensitive, very sensitive to the charge. So even small fluctuations of charges nearby will modify the effective charge on the island. So what we will have then, you have some noise in this axis here. in the horizontal axis, you will have some fluctuations of charges. And in this case, the fluctuations will, if you are here, for example, they very strongly modify the energy level separation between 0 and 1. However, if you are at this point here, exactly at half Cooper pair charge, then you have extremum here for the lowest band and for the higher band. So basically, the energy difference between 0 state and 1 state in this picture will be not changing in the first order. So it will be only changing in the second order. People immediately realized, actually, these people realized that they have to go to this point to observe the coherence oscillations. Because when they were measuring here, they couldn't see anything. The coherence time was much shorter than nanoseconds. So basically, the sweet spot is very, very important for the charge qubit, that you are staying in at the average value of the charge, which is, so to say, immune to charge fluctuations. But of course, only to the first order. And to the second order is not immune anymore. The other source of fluctuations are fluctations of magnetic flux in the squid. What does this magnetic flux in the squid? Of course, where is this energy level separation between the lowest energy state and the first excited state? And you have the variation of the energy level separation. You have basically the phase noise. You have dephasing, because if you prepare the eigenstate of the Hamiltonian and then you start oscillating the energy level to the separation to the higher state, then of course you will have the accumulating phase, and this will lead to dephasing rather than relaxation. So the origin of this flux noise is still debated. It's a big problem in superconducting quantum circuits. There are still some unknown matters in that. What we know now that there are also one of the sources of the charge noise are spins on the interfaces. So you have the interface of a metal, then you have some oxide on the surface, and you have also some contaminates, some adsorbates. And in this adsorbates and contaminates, there will be free spins, in particular hydrogen spins. Water is in any vacuum chamber. If you take some sample of the air, then water very easily goes there. And a single proton, which is the nuclei of a hydrogen atom, will of course have its own properties as a spin. And people have done systematic experiments with superconducting resonators where they saw the appearance of hydrogen spins on the surfaces. So this is one of the origin of the flux noise, but there are also, of course, many others. So there are two types of dephasing, basically the charge noise and the flux noise. One moves fluctuates in this direction, the other one fluctuates in that direction. But more about that we'll talk later on. We'll discuss the coherent sources of superconducting. Any questions? Of course. Хорошо, давайте двигаться дальше. So, stupid people ran to buy expensive pulse generators. Clever people started thinking. And it turns out that thinking is always better than buying something expensive instead of thinking. So this group in France, some famous group, actually, the group led by Michel Devarest at the time and Daniel Estef, both are famous pupils of Anatole Agraval, who was the kind of the pope of nuclear magnetic resonance, French scientist with Russian origins. And Michel Devarest and Daniel Estef, together with the team, with Denis Vion, they were thinking how to make this experiment better. And then they came with the idea that instead of using a single sweet spot, one can use double sweet spot. They came up with the idea to design a circuit where not only the charge fluctuations were where the circuit was not only immune to charge fluctuations in the first order, but also a circuit, such circuit where it was also immune to the flux fluctuations in the first order. And they come up with this circuit here. So instead of using one Josephson junction, they took two Josephson junctions here. So this is a little island here. It's a two Josephson junctions. That's again is the squid. Now, these are shadows of the evaporation. So they were doing this double end evaporation from two sides, and this is just a redundant result of that. Also, this two electrodes is just the same electron, but evaporated in two steps. Anyway, this is the Cooper pair box. These are two junctions here, and this is again the pulse gate. But in addition, they also had a large Josephson junction, which was connected in parallel to small junctions. So instead of having now this is a bulk electrode, they introduced here a large Josephson junction, which phase they could control by applying the current through the junction. And by changing this phase, they were able also to change the phases on these two junctions. So this phase was not anymore free, but it was controlled by the external flux. And the energy level picture is very beautiful here. So this is the energy scale, vertical, but now measured in frequency. This is the charge axis, and this is the phase axis. If you look at the charge axis, basically what you see here is the frequency of the transition between the 0 state and 1 state. You see it's 0-1 transition. And it's minimal at half Cooper pair charge as before. And then if you move away from half Cooper pair charge, then the frequency increases, but of course, also the influence of charge losses increases. So you have to stay somewhere around this charge, which means along this line. But then in addition to that, you also have the phase or this flux variable, which is now controlled by a large junction. It's not only the external flux, but also the flux which you can control by the external current applied to this junction. Again, I show this picture again. So this is this junction here. And you apply this with current, and you suppress the quantum fluctuations in this junction by using two large capacitors. So you basically make the charging energy of this whole device very low. The capacitance of this part is very, very large, and therefore the charging energy is tiny. Quantum fluctuations are basically absent. Yeah. And then you go with this phase. You go to the point where it has this extreme here. This is the dependence of, this is the generalization of Hamiltonian now in two dimension, basically charge and phase. And there is another extreme here. There is a saddle point where you remain effectively insensitive to the charge, and also you may remain to the first order insensitive to the fluctuations of the flux. And just by doing this clever step, they immediately saw the increase of the coherence time. So the relaxation time T1 was up to almost 2 microseconds, and the coherence time T2 was half a microsecond. Factor of 1,000 improved just by clever thinking. And of course, you don't need any more of these expensive pulse generators, which other people went to buy. So basically, you see that with this type of good coherence, you can use very cheap pulse generator, which can make pulses, let's say, in the range of a few nanoseconds. And now this is what you see on top is the Rabi oscillation. So we apply the frequency, in this case, particular case, about 18 gigahertz, somewhere here. So in this case, you drive the transition between 0 and 1. This is 0-1 transition. Then the population of the excited state, once you measure the charge in the ion, oscillates as a function of time. This is Rabi oscillations. And the oscillation period in this particular example is about 100 nanoseconds. And if you increase the amplitude of the driving microwave field, then the Rabi oscillation frequency goes up. You see the Rabi oscillation frequency here goes up from a few megahertz to a few tens of megahertz. And the smoking gun, дымящееся ружье индейцев, ковбой, говорят по-английски, это smoking gun. Smoking gun of Rabi oscillations of a two-level system is that the Rabi oscillation frequency is exactly proportional to the amplitude of the electromagnetic field which you apply. if you take a phase cube and you drive a car, it has also higher limits. And interestingly, actually, there is a very classical analog of drive oscillations, which is beating. I can explain to you how to observe drive oscillations and spin echo and random changes, everything classically. It's just physics of nonlinear oscillation. However, if you have this proportionality exactly proportional to the amplitude of the drive, then there is no doubt, and this has been proved by calculations that you are dealing with the two-level quantum system. And this was important because that time people really still macroscopic circuits behaving as quantum objects. And then here you have also another example of the So those who are complaining against English, the question is in Russian, please. Okay. So this is the story which I told you up to the year 2002 or so, about 20 years ago, when the whole field started. And then once physicists saw that circuits can be quantum coherent, it opened the whole range, beautiful range of ideas. Basically, what we have here, you have a handmade circuit which behaves quantum mechanically as an artificial atom. This was that time very weird and difficult to believe. But there are many questions, of course. How far does this equivalency goes? What are the differences of these artificial atoms from natural atoms? Can you do here various quantum optics experiments which people have done with natural atoms and so forth? And one of the key differences of surface, and that's why the physics is very interesting, is that the electric dipole moment, also magnetic dipole moment of a surface can be made arbitrarily large compared to nature. In nature, the dipole moment of an atom is very small, and you could make it a bit larger by making a Rydberg atom, what we discussed already at the beginning of this lecture. You could excite the atom to some high energy state, and then its effective size becomes in micrometer range, and dipole moment is large. But nevertheless, it's still not arbitrarily large. Here, the situation is such that you can make the dipole moment really huge, and you can make the interaction of the two-level system with electromagnetic waves extremely strong. So you cannot even then distinguish where the excitation is it in the atom or is it in the wave, in the environment. So there are other examples like polaronic excitations and so on, where you have basically some localized electric field, and then you can quantize this field and get an elementary energy scale and talk about these quantum excitations. But understanding of that actually took some time, and the key development in this field was the invention of the circuit QED. You may have heard of QED. This is an abbreviation of quantum electrodynamics. And quantum electrodynamics typically was a term discussing the properties of atoms in cavities, or properties of atoms in free space. But now you have not an atom, you have an artificial atom. You have a nonlinear system which you drive not by light, by visible light, but you drive it by microwaves. So the energy of photons is much lower, roughly 1 million times lower than the energy of visible light photons. However, you can also try to do similar experiments with that. And this approach actually came up with the idea of using the circuits to do the QED. Historically, that time already in atomic physics, people knew that one can manipulate atoms with light and also with microwaves. If one discusses Rydberg atoms, of course, one can also apply microwaves because transition energy between neighboring states in the microwave range. And what people were doing, they were putting an atom in an electrodynamic cavity. This is a cavity which resonates at a frequency, let's say, few gigahertz, microwave frequency. And then if you put an atom there, and you consider there some fine splitting or hyperfine splitting, which will be in the gigahertz range, then the atom interacts with electromagnetic field in the cavity. And one obvious thing is that if you have a transition energy between atomic levels in resonance with the cavity photons, then obviously the atom will immediately give the energy away and we will relax with the lower energy state. This is so-called Purcell effect. The cavity provokes the decay of the atom. However, if you are detuned from the cavity frequency, then the atom will not relax because it doesn't have any modes to relax in the environment. However, the atom can be polarized, and therefore it modifies the electromagnetic environment here. And the qualitative effect which appears in the cavity QED, cavity quantum electrodynamics, is that by exciting an atom from the ground state to the excited state, one slightly modifies the resonance frequency of the cavity. So if you have a resonance frequency of the cavity and the atom goes from ground state to the excited state, it changes the effective dipole, properties of the cavity, and therefore the resonance frequency is shifted. That means you can measure, for example, the resonance in the cavity using photons which have nothing to do with the frequency of the transition in the atom. However, these photons will have in the resonance, they will have certain phase and certain amplitude of the magnetic field. So this will be classical field, doesn't have to be quantum field. And if the resonance frequency of the cavity changes, then it tells us that the atom is excited from the ground state to the excited state or other way around. And this is an approach which has been actually brought up in quantum optics long before the appearance of superconducting qubits. We talked about this very briefly already when we discussed the readout of atoms and so forth. And the model here is described by the so-called James-Cummings Hamiltonian, which is written here. It has three groups of terms. One is the photons in the cavity. The other one is the photon in an atom, or excitation in an atom. Can be in two states, and this is sigma z matrix representation. And then there is a coupling between cavity and qubit. Now, this Hamiltonian is written in the approximation, which is so-called rotating wave approximation, where the fast rotating terms have been dropped down. To save it, I will tell a bit more about that in the near future, in the next slides. Now, cavity QED with atoms, you see there was already a long review written by Jean-Michel Raymond already in the beginning of 2000. So there were many experiments done in the 90s with this thing. And basically the idea was that one can prepare some atoms in some oven, and then they can be excited by laser or microwave. When they enter the cavity, they undergo Rabi oscillations. But Rabi oscillations of different nature, not the Rabi oscillations I told you under the effect of the external field. If you bring an atom in the excited state in the cavity, the atom and cavity form a coupled quantum system. So then the two states of the atom will have, under assumption that they will have the same energy, the generosity will be lifted. And therefore, the atom basically will oscillate between the two states. So in the effective picture is that when the atom enters in the excited state, it is an excited state, it enters the cavity, it will give the excitation away to the cavity, and then the cavity will give the excitation back to the atom. And this will continue. This is so-called radio oscillations, the exchange of the excitation between two-level system and a cavity. Cavity is a multi-level system, of course, but since the excitation in the atom is quantized, this excitation will not disappear completely. So it will just continue exchanging the energy between the two parts of the coupled system. And if you measure the resonance state of the cavity, you can determine, depending on the time of the duration of the interaction, these atoms, they take some time to go through the cavity. So if the atoms move faster, then the resulting state of the atom is going to be periodically depending on the time of flight here. And these are coherent oscillations, vacuum radio oscillations, which were measured with atoms. That's where the photon is in the atom, and this photon in the cavity, again photon in the atom, photon in the cavity, photon in the atom, photon in the cavity. Of course, the oscillations were decaying here, but the time here was measured with atoms. You see the coherence was really very, very good. Now, if one describes the system by the James-Cummings Hamiltonian, this is also can be visualized in the form of the energy levels, and sometimes people call this picture James-Cummings ladder. So this is the atom, which can take state 0 and 1, and this is the cavity. Of course, there are also states 3, 4, and so forth. There are infinitely large number of states here, all equidistant in energy. However, if you have the interaction of the dipole moment of an atom with the cavity, then this state where you have one excitation in the cavity and no excitation in the qubit, it will be, the generosity will be lifted here. And then you have two states where the cavity frequency is basically shifted and the atom state is also shifted. So these are kind of two parts which are interacting and affecting each other. The experiment with atoms is usually done like this. This is the example of the optical cavity where you use optical photons for this kind of experiment. These are nano cavities which are used there. And this is the example where you use basically the cesium atoms here, which are going down in this cavity, and then the probe laser measures them by fluorescence, either in the ground or excited state, depending on the time of the interaction. That's another example of similar, and this is a kind of optical cavity QED, which was pioneered by a number of people. This review is by Chris Monroe. 2012, 10 years ago, there was a Nobel Prize given to this story about atoms and cavities, and it was given by Serge Haroche, who is in Paris in the École Normale Supérieure, and David Wineland, who is in Washington, D.C., at NIST, if I recall correctly. So basically, this was a Nobel Prize given for groundbreaking experiments that enable measuring and manipulation of individual quantum systems. If you want, this was the beginning of the quantum revolution 2.0. So people distinguish between quantum revolution of the previous century, where quantum theory allowed to understand transistors, allowed to understand solids, the solid properties, and this was only possible because quantum mechanics was actually ruling the game in solids, and this has led to quantum devices. People call them quantum devices, but they're not quantum devices of individual quantum systems. They're quantum devices with many, many electrons which interact with the lattice. This was the beginning of the era of the which sometimes people call quantum revolution 2.0, where one can actually manipulate individual quantum degrees of freedom of an atom or maybe a cavity, and or maybe things like this ions in the should be trapped ions, of course, not atoms, but the atoms are ions of undressed atoms, so to say. All right, now this is again the picture. There are some interesting review and so forth. I will only mention that in this model, which rules the game, then there will be splitting also in the higher states. And here, if you go up with the number of state, then the splitting goes as square root of the number of state in the cavity. Now, I'm telling you this story as a preamble to the pioneering experiments which were done with superconducting circuits at Yale University. And this was done in the group of Rob Shelkoff by this young gentleman, Andreas Wader. Andreas was my PhD student, and he did his PhD with me, working on completely different subject, actually on quantum subject, but not on the cavity. But here the passion in quantum optics was one of his hobbies during his studies in Aachen. And after completing his PhD, he actually spent some time to publish a appropriate Nature paper about the vortex tunneling. But then he left as a postdoc to work with Rob Shelkoff in Yale. And this was exactly the right experiment, right moment when this experiment should have been done. Basically, they've done an experiment which is simply translates what was done already that time with atoms by Haroche, Wineland, and others, but to the superconducting world. And what they have done is the following. So they prepared a cavity, which was basically a central wire of coplanar waveguide transmission line. So this is the ground electrode. So basically, it's all lies on the silicon substrate or sapphire substrate. Doesn't matter. This is the ground. This is again the ground. And then you send a signal of some 10 gigahertz in this transmission line. So the signal propagates here, and this is the ground. It's like a coaxial cable, which is flattened on the surface. По-русски это называется щелевая линия, coplanar waveguide, or bicoplanar waveguide, because it has two grounds here on two sides. And then you calculate your structure such that the impedance here will be 50 ohms. And then you can couple the signal from coaxial cable to this transmission line on chip, and the signal will propagate on chip, being impedance matched. But then when you make a gap here, and then a gap there, this piece becomes a resonator. So the signals will be reflected from this side and reflected from that side. And in this resonator, there will be standing waves. So what you see here is a standing wave. What will be the lowest frequency of the standing wave? Какая будет самая низкая частота? Половина длины волны, совершенно верно. А то, что мы видим здесь, это полная длина волны. Half period is like this, and half period is like that. So this is the full wavelength. This is the second mode, just the second mode of the cavity. So cavity, this kind of cavity is not a lump cavity, it's a distributed cavity, and therefore it has half wavelength resonance at the lowest frequency, at twice the frequency it has full wavelength resonance. Next will be 3 halves wavelength resonance and so forth. And if you put here a superconducting circuit, in this example, this is a Cooper pair box. This is a Cooper pair box connected by 2 superconducting electrodes to the bulk superconductor here. And this is a little hole which can be used to control the flux, changing the Josephson coupling energy between this box and the ground. So this is basically an artificial atom which is sitting close to the cavity. And because in the standing wave in the cavity there will be nodes and antinodes, узлы и nodes and antinodes of the standing wave. On the electric field, where is the antinode? Of the electric field at the ends, exactly, because there is no current flow in there. Magnetic field is 0. There is only polarized charge, which is accumulated there. And therefore, the maximum electric field will be at the end of the cavity. But if you use the second mode, then of course it will be another maximum of electric field in the middle of the cavity, right? So, and if you use the fundamental mode, then it's only on the very ends. And basically, this oscillating electric field will couple here to the artificial atom, and change of the dipole moment of the artificial atom should change the resonance frequency. So basically, this is the experiment which they have done. They took exactly the Cooper pair box of Nakamura and company, and then measured it in a different fashion by using not readout of the charge, but rather reading out the signal on the cavity. So you do it in the following way: you adjust the system to have some resonant transition between 0 and 1. Let's say it's 7 gigahertz, and then you have this cavity mode, for example, 10 gigahertz. And you measure when you measure the transition to the cavity, you measure the peak in the transmission, exactly the resonance frequency. If you measure the phase of the transmitted signal, then it changes from 0 to 2 pi at the resonance. So you can use both the amplitude or the phase measurement to see a tiny shift of the frequency, resonance frequency of the cavity, depending on the state of the cavity. It's a very beautiful, simple experiment. It's like, sometimes I give this example. У вас есть труба органа, которая имеет какую-то резонансную частоту. Дальше у вас на эту трубу садится муха. Если муха села, то частота немножко сдвигается. Если мухи нет, частота та, которая должна быть. Так вот, муху, севшую на резонансную трубу, здесь можно в этом эксперименте увидеть, просто наблюдая сдвиг частоты резонанса, как функция состояния этой системы. Если здесь есть возбужденное состояние, дипольный момент отличается от дипольного момента в основном состоянии. Поэтому фактически мы не разрушаем квантовое состояние этого искусственного атома, меряя резонансную частоту вот такого связанного с ним осциллятора. Any questions? Looks like we have to stop now, which is good, because I think I'm going to explain to you a bit more detail on the cavity QED.